Good morning, good afternoon, and good evening, wherever you are. Thank you for joining. At CIQ, we're focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Aptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source. Happy Monday.
Monday? Jeez, Louise, over here. I actually had to stop and think about that for a moment. I'm like, wait, where am I? What time is it? What's happening?
Thursday. It is the 18th of January, 2024. The 18th.
So I just want you to know that people can actually see you behind the scenes before we come live here. I was just notified that someone was watching me rock out to our CIQ music. That's super embarrassing, but also funny and awesome.
I'm pretty sure you've been warned.
You know, that's true. That's true. Then they're always watching, right?
Always. They know who they are.
That's awesome.
They know who they are.
So speaking
Welcome,
of
everybody.
Watching, yeah, we've got like a whole cool crew coming on here. Very exciting. Hello, my friends. Gary, so good to see you again.
It's been a while, Gary. How are you? Happy New Year.
Hey.
All right. So you actually have a really nice long description of what you do. I love that. Do you want to just kind of like say hi and tell people what you're doing in the world?
Me?
Yeah.
Oh, well, I'm the science IT department head over at Berkeley Laboratory, and the portfolio of things that I do include managing the institutional high-performance computing and related services for scientific computing. And I'm also the HPC manager for the institutional HPC down at UC Berkeley.
Awesome.
Very cool.
Yeah, glad that you're here. Brian, you want to say hi and tell us who you are?
Hey everyone, good to be back on the webinar. My name is Brian Finn. I'm a solutions architect here at CIQ. Backgrounds in HPC administration and architecture, and excited to talk about benchmarking and performance today.
Yeah. Jonathan?
Man, my story is the same as Brian's. I'm a solutions architect here with CIQ, background in HPC. Excited to talk about performance.
That's awesome. Next time you just be like, yeah, what he said.
What he said.
What he said, ditto. Awesome. Forrest, what's up, man?
Good morning, all. Oh my gosh, I just realized that my microphone was on. Good morning, everyone. My name
Forrest singing.
Whoops. Good morning, all. My name is Forrest Burt. I'm a solutions architect here along with Jonathan and Brian. So, what these guys are up to. Good to see you all.
Very cool.
Very, very cool. And Zane, I mean, I don't think you need an introduction.
I'm Zane.
Man.
I work
Everybody
here at CIQ.
knows the Zane. Oh, dang! Alan in the house too. All right, you got to introduce yourself now.
Yeah.
Sweater on the
Me introduce myself to you guys?
Yeah.
I think you could read my bio at this point.
Oh, is that what you would like me to do? Okay, next time, Alan, I will come prepared and read it for you.
Oh, we should do it like Stephen Colbert does with the puppy introductions, right? Make it up.
I could do that.
That would be fun too. Like where we met, right? And just make it up. Where do you know this guy from? Well, we were on the moon having tea.
Yeah, right.
Call out the wrong university. That can be fun. If you don't mind, Alan, it's 2024. We have to reintroduce ourselves.
I know.
Happy New Year.
Yours.
Yeah. Yeah. Everybody else in my life seems to have Alzheimer's. It's like the state wants me to register my car again. They forgot that I registered it last year. And then there's the training. Oh, don't get me started on the training. Gary knows what I'm talking about.
It's already time for annual training. Awesome. Gary's laughing. He knows.
Okay,
what are we talking about today?
Alan is awesome, and he is head of the HPC department and a good partner of ours at Texas Tech. And what is the NSF CAC?
The National Science Foundation Cloud and Autonomic Computing Center. I had to practice for 2 years to learn how to say autonomic. But basically, it was a combination of two other centers, one we proposed focused on cloud standards, and another that was working in the area of autonomic computing, an area that IBM kind of popularized. The idea was self-healing stuff, self-managing. So we just usually say cloud and highly automated computing.
Awesome. Thank you for that. Thanks everyone for being here. Very glad that you were here. So today we're talking about code to conquer, best practices for achieving peak performance in HPC systems. So I have just kind of like a lead question. Is it always speed? Because that's what I think of like peak performance.
Alan came off mute real quick.
Yeah, whenever I think about performance, I think about reliability.
Okay.
And one of the key barriers in a lot of, especially, university scale systems is keeping all the hardware tuned up and functioning to the point where it's not tripping over itself. I actually don't know how the really large outfits manage this, though I have to confess to having been very impressed when I went through Microsoft's Azure Lustre setup. So, reliability in the sense of being able to find and eliminate things that, error rates might cut into your performance in ways that never let you achieve it. I guess the place that a lot of people encounter this for the first time is they buy their brand new cluster and they turn it on and they want to do an HPL run, or HPCG, or, benchmark it. And that one node is just acting up. Why can't you just lock it out of the run and you publish that result? So, yes, just raw speed is important, but to get to that speed, you have to have highly tuned up systems.
Gary.
Yeah, I'm just going to chime in with Alan and just say it's a proxy for a lot of things, but maybe, I mean, I don't know if this is a good analogy, but it's like getting, say, a performance sports car or something, and it seems fast to you, but is it really that fast? And in this case, you want to get your money's worth because you had purchased, you spent big investment, and if it's not performing, then you're not making use of the investment. And so, in fact, if it works for you, then you probably could have got away with a smaller system if it wasn't performing at peak performance. So peak performance is just kind of a proxy for a number of things, which, some of which Alan enumerated.
Brian, you said benchmarking first. What are your thoughts?
So when I think about performance, I mainly think about time to results from like a user perspective. And this could be whether you're on the enterprise side doing product development, like having a faster time to result, it gives you that competitive edge to be first to market. And on the research side, getting your results faster allows you to put together your paper together and submit it. And basically, these papers have deadlines and you want your results fast to meet that deadline, basically.
Jonathan? You're smirking.
Am I smirking?
You're smirking.
I don't think I'm smirking.
I think you are.
Okay. So all of this is true. Alan and Gary's comments both about kind of systems reliability and actually being able to deliver the performance that the system has available, or in theory has, to me is founded on this understanding that an HPC system is not just one thing with one performance profile, but it's a large, interconnected, complex system. And that can lead to things like interesting failure scenarios or unexpected problems where some part of the system goes wrong and maybe you cordon off that part to get the performance you want out of the part that's working well. But it also means that there are many opportunities for kind of very subsystem dependent bottlenecks within your system. And, when you design a system, you try and make sure that it's well balanced and you don't have like a really coarse example might be you don't have CPUs that are very fast but not have the memory bandwidth that's available to keep the CPU fed with instructions and data to be processing. But that same thing is true throughout the system, from things as normal as the data system, the I/O system, maybe network, but I think a lot about storage performance. I had a site that I was at one time where we like 10x'd their performance by going from a disk-based GPFS system to a flash-based GPFS system. This was at the very early days of where NVMe might be a thing you would even consider doing, and we had some somewhat bespoke hardware for doing that in this environment. My like wanting everything to be perfect mind wants to say just re-architect your application so that it doesn't do all that I/O, so that the I/O is better characterized. But the end result was we made this one change. We spent, a chunk of money, and then everyone's performance was faster. So you can address that kind of a bottleneck from the system side, or from, if you're on the application side, you can try coding around it. But there are also things as mundane as the queuing system can introduce bottlenecks. So if I think a lot about the difference between high performance computing, where you have like one big job that's going to run across a big chunk of the system or the whole system, and what in my mind is high throughput computing, where you have tens, hundreds, thousands of small single node or even single core processes that maybe run for a very short period of time. And in that high throughput computing workflow especially, your queuing system can introduce significant bottlenecks just in the scheduling and getting processes out to the machine so that there can even be something that runs. And this is something we don't generally think of as the performance of the machine, but to Brian's point, time to result is really all that the user cares about. And they don't care whether the system is slow because it took a while for the job to get out onto the system and run, or if it was because it was slow when it was running. They just know how long it takes for them to get their result.
Yeah, an example of that would be a typical learning curve for people running on a cluster of suppose you're launching a large number of jobs. Do you do them as array jobs? Do you do them as how do you count the number of cores and optimize that? What if you have variable core requirements at different phases of the job? So yeah, I think this all gets lumped under your scheduling thing, but I want to go back and emphasize reliability once more time, because I know I said it before, but when we invested over $1.5 million on improving our power and cooling setup, we just had better uptime, and that's performance also.
You guys keep taking all of my bullet points here. Whenever I was thinking about this, I started writing down the different things that I wanted to hit on, and I think now you've hit on most of them. We'll just have to dive into them. Forrest, before I start diving into that, do you have anything to add?
Nope, for the most part, I would just echo what everyone has said here. In my experience, users, when it comes to the performance of the system, are mostly concerned with being able to make efficient use of time before, as Brian notes, those deadlines for papers, conference submissions, stuff like that. So being able to have a system that is not only decreasing that time to result, but is highly available in the meantime. I know I always remember, the cluster goes down for, and this was very rare, but on the rare occasions, the cluster went down for a second. We immediately had people, banging down the door like, hey, I've got this deadline coming up. What's going on? So yeah, just like Alan notes, even investments in cooling, stuff like that, whatever ends up not only speeding up on, a core, individual system, faster memory, that type of thing. That's definitely something to consider. Like, those things are going to directly affect the speed of a result. But then those I shouldn't say intangibles, but those other tangible things that increase just the availability of that speed to everyone is just as equally as important as having a fast system itself.
So I'm going to read you my list of ones that I put together. And one of them I put in there, I wouldn't have thought about it, but I started thinking, what is Alan going to say? Or what's something that he would go to? So I had code optimization, which I think we've already hit on. IO optimization. Jonathan, you hit on that one. Workflow optimization, which I think is important for everybody. Energy efficiency was the one that I knew Alan would probably bring up, and he did. And then monitoring and profiling. Those are the ones that I really thought were important. So let's dive into each one. So I know we talked a little bit, Jonathan, about I/O optimization. I think there's a lot of things to be talked about around that, and where data lives can impact that. Let's talk more about that, if you don't mind.
Yeah, so like in the olden days of my experience, which isn't that long ago, but a big part of it was separating out your metadata from your data storage, and this is especially when you have relatively low performant from from a latency perspective disk storage. You wanted to save your disk for kind of large, bulk, well-characterized I/O, and your file system would help with that. But maybe you have tens of thousands of files in a directory, and that's a lot of load, a lot of small IOPS load on your file system. So major parallel file systems like GPFS and Lustre would give you an opportunity to separate that metadata out to something that was better for that latency. So originally that was maybe you had 10K SAS hard drives with a RAID 1 mirror for that, or a stripe of RAID 1 mirrors, a RAID 10. To do that these days, almost anyone, if not literally anyone, would put that on some kind of NVMe storage just to get that near memory speed for doing that kind of metadata operation. But increasingly, it's kind of all going flash. We see, one of our partners, Vast, has a really cool story around how to characterize with your file system your workload to fit well on different classes of solid state disk or solid state storage, I guess. And so a lot of that is going away, but it still is useful to just keep track of, from an application standpoint, what I/O your application is doing and how it's mapping to all of the different processes you have running. If everyone is kind of thundering herd onto one location, or if you're spreading your metadata load out. I don't have as much experience from the application side. I'm very interested to hear what Gary and Alan's experiences are in this. I just see the horror stories of a Lustre system having been knocked over and lying on the ground in shambles.
Yeah, so I almost feel like this.
Sorry, Alan.
Sorry, I thought I was being asked.
No, absolutely, go for it.
I almost feel like we need a GitHub repository to go with this this series, so we can share code. I have a bunch of scripts that just sample I/O from each node and aggregate it up. And we've been working with a vendor to get MPI versus data I/O bandwidth separately. It's not quite ready for release yet. But in general, I think we have a lot of tools for CPU profiling, even GPU profiling, but not many tools for I/O profiling that stand the test of time, other than just benchmarking the system. We actually just upgraded the I/O monitoring software, and we bought a new storage system using a vendor product. So I'm looking forward to that. Slurm can report I/O statistics. Many schedulers can report I/O statistics, but I found it better to have real-time monitors that give me I can actually ask the cluster which account is drawing the most I/O and from which nodes and what are the highest I/O commands. So yeah, like I said, we should have a GitHub repository where we can share these things.
Gary?
Well, we've noticed over, and I'm sure everybody has, but over the last 5 years, the mix of jobs has gone from which used to be mostly MPI and some Python to almost mostly Python. And then the way Python hits the parallel file system with all its files in an environment, we just noticed that the high watermark on our parallel file system was pegged. The performance was pegged all the time because of all these files from people firing up Python jobs. So, so one thing that we do is, have people use Apptainer to stick it into a container, and that helps out tremendously for that small I/O. And then more recently, we've been looking at we've installed a number of these VAST systems, and they've been really good at like life science workloads, which are can be kind of pathologic in the way they tank the performance. So, but out of the box without any tuning, we've had really good success with the VAST systems for using life sciences workloads. And then I'm just thinking as we're talking about that, while Jonathan was talking about like how a scheduler performance can make a difference. I do remember different versions of schedulers, how fast they spawn the jobs can, that can make a difference if the jobs are like super short for like genomics workloads. So then all of the time is in like how fast it actually spawns the jobs. So that makes a difference. But if we're talking about code optimization, that's a really tough thing because then it's more like hand-to-hand combat with the users, that you're not turning one big knob and speeding everything up. You actually have to go out and work with these users. And so we've been focusing on that at Berkeley Lab quite a bit. So I have these 3 consultants and we put out things like, is your Python code running slow? And then we're just going to kind of knock these out. And then to entice people to do this, because then it benefits everybody, including your investment. We give out allocations here, and to get people to come in, we just said, look, you come by our office hours for a tune-up on your code, and we'll give you 10,000 hours on the system for just coming in. And you can come in as often as you'd like, and you can get that. But we want to create. Otherwise, if you ask them to do it on their own, they won't. So, so we're trying to entice people to do that so that we can work on that end of it.
Yeah, code optimization to me is interesting just because do you have people that come in that really don't know what they're doing at all? They've never done this. They just assume they can consume everything on the environment. And then how do you combat that? I'm assuming you can do that with some of the schedulers. You can lock them into a very specific set of things that they can consume, but does that always happen? Brian's laughing.
Brian is like, yeah, he's like,
yeah, Brian's laughing.
I mean, you would be surprised the people that we talk to that are responsible for their HPC environment at wherever they work and have no idea what to do with it. They're like, it's great when it works, and when it doesn't, I don't really know what to do. And that's pretty common, right? So
it's probably why Brian's laughing.
Yeah. Yeah. He's like, yeah, that's what I do. I come in and I fix the problem. I spin up a little HPC environment with our HPC stack here at CIQ, press the button, and go. I mean, that's a little simplified, but come off from you, Brian. Tell us your story.
Just anecdotally from my experience, with on-prem systems, typically, I guess partitioning of the system wasn't done well in the beginning, and basically a lot of the jobs that were running from the various development groups were just extremely inefficient. And just from making changes to like your scheduler configuration, there was significant improvement with user workflows. They were just getting scheduled a lot faster, and the users were happy after that. Yes.
Very, very happy. Very happy.
Running, users happy. Yes.
Yeah. So this actually kind of goes into a question. Did you want to touch on that real quick, Jonathan? Because the question actually kind of goes into this.
So yeah, behind the scenes, everyone, we've got a chat here where we're kind of sharing thoughts and potential things to talk about. And I'm noticing Alan here talking about a number of very specialized things you can do to minimize startup time as one aspect of performance. And it makes me think about, there's always like more bespoke, more specialized things that you can do if you know your workload, you know your users, and you know that it fits well for them, and they can do that. And that's part of the issue here, I think, when we have conversations like this about HPC. And the question that was just on the screen for a moment is there like a documented process for doing this right and getting this all correct in the first place? And part of the problem is there isn't just one answer, and it's an optimization problem against what it is you want to be doing. If you have a single problem that works really well on a single, like, multi-processor but single socket or dual socket system, now a single memory domain, and that's all you need, maybe you don't need a cluster. Maybe you need one big server, or maybe you need a bunch of GPUs in a big server, that kind of thing. If you need a cluster and you know that you have some MPI workloads, let's say, that you're going to run, you can get pretty far by just having some OmniPath or some InfiniBand and some relatively new decent servers on a network, and then running Slurm and just running stuff on it. But a lot of this conversation is run by large sites that are optimizing the last bit of performance out of every dollar that they spent, because every bit of performance optimization that they get out of it saves them a force multiplier's worth of time for all of their users on this huge system. So I think really the summary of what I'm thinking is a lot of this conversation makes it seem like if you don't get it right, you're just leaving money on the table. If you don't get it right, you're wasting your time or your effort. But this can be complex, but there's a lot of ways for it to go right too, not just a lot of ways for it to go wrong. And you can get a lot of work done, and people in research have been getting a lot of work done with a stack of desktops in a closet. And it's always a process of iteration and learning and just making it a little bit better all the time. You almost never will get it just right from the beginning.
Yeah, good point. I saw you come off mute, Alan. Go ahead.
Yeah, so I want to pick up on what John said. I think the question is how to go from 0 to hero. Well, hero, fortunately, is a fairly achievable state in HPC. I mean, it is an area that, generally speaking, if you can at all keep the machines busy, it's usually pretty productive. I mean, just as a blanket statement. I think academic outfits that have well-equipped HPC and academic research computing centers. I have a whole set of lectures I give about talking to upper administration about return on investment. And usually all you really need to do is to document what you're doing, because it ends up supporting a lot of research. It ends up supporting a lot of classroom instruction. And if you just write it down, often your conversations with administrators are easier, because also when you list the researchers, they're good at spotting the vocal faculty members in the list and thinking, oh, I don't want to get that person upset. So you can use the system to your advantage to some degree. In a business setting, HPC I think also can be shown dollars and cents to be very productive. So I think it also goes back to what Jonathan and Zane were saying, that just getting it running can be good enough at some point. Then you can learn as you go. The premise of this particular call, though, is how do you get the maximum performance out of it? And I think the question centers on that as well. So I would give some social advice. You're not the only person in the world doing this. You reach out to other people who are doing it. This webinar is maybe one way. There are forums. I guess you guys can put a link to your forums in your chat there. And beyond the CIQ viewpoint, that is, in academia, we have the Campus Champions. We have an organization called CARC, C-A-R-C-C, Campus Academic Research Computing Consortium. In a very general way, we started about a year ago the HPC.social set of forums. It's got Slack and Discord and Mastodon and projects, and it's even got a good first projects page. If you go to hpc.social and look at the projects, there's maybe I don't know how to get started doing HPC computing. Well, you can just contribute to one of a couple hundred projects that are listed there. Just find one that so you're not the only person in the world doing this, and reaching out to other people, comparing notes, I think is a good piece of and as important, or maybe more important in some settings, than actually just massaging the hardware.
Thank you for throwing up those links. Thanks for pointing that out, Alan. You beat me to it. I was going to say hpc.social too.
Ooh, Jonathan Maple, hey. It's also an optimization of the users too, and how they choose to leverage what is deployed, like ISV versus recompile and go, or architect.
Yeah, and alongside, if I haven't missed something there, a lot of that goes with training too, and I think a few examples of best practices, and I know like that's the point here. Gary was talking, for example, if you have a Python code and it's running slowly, these are reasons that it might be slow. Here's a possible solution: use Aptainer to containerize it because it helps the small file I/O. Demonstrating that to users and showing the benefit. I think one of the issues for me, again, coming not from an applications perspective, is how do we even know when something is slow? Maybe someone's running their code and they're satisfied with the performance and they don't know if they made a small change that they could get a 2x performance improvement. Have any of you ever had any experience with how you help a user identify whether their code could be optimized or not?
This is a really, really good question. I think a lot of people are curious. How do you know? Forrest, you have an idea?
I recall that after about 3 or so days of a job sitting on the queuing system from a user who I knew was very new on the system, I kind of got an odd suspicion that something might be up, and SSH'd into the nodes and found that it's sitting there, via HTOP. There's nothing. It's not doing anything. The CPUs, all the nodes are completely idle. It's basically just taking up, 3 empty nodes. So I got back in touch with them and was like, hey, just so you know, I canceled this because this isn't doing anything. And we ended up getting back in touch with them, got it optimized, got it working. But just kind of like being aware of your users and their experience levels and kind of who they are. This in particular was a user who I knew had just come in on like a summer research program. And so I was like, I about guarantee this person knows very little about HPC. So just kind of, keeping an eye on those new users, looking for those kind of, smells of something wrong, like things that are sitting for days on end, but that don't seem to, be completing. There's no new jobs coming up, things like that. It just gave me an odd feeling. So, but that type of thing, knowing your users, knowing who's new, knowing who might need help, and kind of connecting that to what's going on in the queue.
Gary?
Yeah, as I mentioned, we have consultants to help users. And so, and we just find a lot of, in our case, they're researchers or scientists, and their specialty is not programming. And so they're not familiar with, these different versions of Python libraries, which would be better for them. And so a lot of times we could able to have quick wins by just say, if you should use this instead. And then we just recently did something for somebody and got a 33x speed up. So, I think a lot of people who are new to programming, because we're reaching, everybody's using computing now, and especially with AI, we do help with people using which AI framework and how they may want to do that. We get a lot of consulting questions about that too. So that's a big part of what we do now is the consulting. And then on the user side, for user training, I heard somebody mention something about training. A lot of people they may know how to submit the job, but they don't know a lot of the other commands. So we have specific training courses where we give like tips and tricks, how to get the most out of the scheduler. And that's helpful too, because a lot of times they don't, they overestimate the time it takes to run the job, and if they had just submitted with a shorter time, they could have got the job to run. So that we've gotten good uptake on that class too. But yeah, I think that's it's worthwhile. People appreciate it. People really appreciate it.
Gary,
yeah,
if
Gary's
I may,
Gary's got a bigger outfit than I do, but we rely on a lot of automation to spot problems we have just a handful of staff. And yes, we do the sort of thing that Gary does. And I tell them, within 3 sentences, the researchers are going to expect you to know their entire field and why their code is running slow or why they're stuck on this. And if you don't like that kind of challenge, you should find another way to be happy. But if you do, this is the spot for you. But sorry, I interrupted you, John.
Well, I think you've actually kind of given the next step there, and what I was going to ask about a follow-up. You said you have automation that helps you identify people that might benefit from that consulting. Can you talk more about that automation and what it's looking for, and how that feeds into your process?
Yeah, it's been a work in progress at the CSC, the Cloud and Autonomous Computing Center, with industry support for about half a decade now. It started with some vendor work on actually on performance. And I gave a link, I don't know if we posted it, but it's the iData Visualization Lab.github.io/HPCC. This shows some of the visualization and automation work. It mines data from the baseboard management controllers at very high speed using redfish telemetry. So we get, instead of once every few seconds, we get, up to 100 hertz of information if we want it. We dial it back if we need to, but it's done by telemetry, so it's server pushed, and it doesn't have much impact on our network at all. And we combine that with scheduler information in various ways, and the various my experience working with visualization scientists has been amazing, because they find ways of looking at your data that you would never have thought of. And they have all these Sankey graphs and radar charts and stuff like that. And so it's mostly been a demonstration project of what you can do. But for example, we were able to spot a researcher whose jobs were very compute intensive for a while, and then they waited for like 20 minutes, and then they were very compute intensive, and they were big jobs that took a lot of nodes. And we found that he was doing something not very clever with the IO in between these computational phases, and we were able to improve that. So this is automated in the sense that it automatically sorts by user, no matter where the user's jobs are across the node, or you can find all the nodes participating in the job, or and sometimes they'll come up with a graph, and I'll think, how on earth would I use that? But I just put it out. We also gave a talk a couple of years ago at Supercomputing on this that was very well attended. And the code is available on GitHub as well. So now the gotcha is that we do depend on this high-speed monitoring for the baseboard management controller, and that, generally speaking, for most vendors, is something you'll have to upgrade your license to get. One of the annoying things about dealing with vendors.
It's true. So there's a question from Dave. Dave, welcome. Good to see you again. I think it's an interesting question too, because it also kind of drives the flipping this entire conversation upside down and saying, is it different if we're talking about cloud? There's a lot of HPC stuff that happens in cloud that maybe it's not viewed as HPC, especially around AI today. But his question is, do you find that more jobs are run on in-house hardware, leased hardware farms, or the big cloud providers for each of these use cases? Forrest, I know you're interested in this. AI, cloud.
A lot of the stuff in AI is going on in the cloud just because kind of as that scales up so rapidly, that's the easiest way to get access to the underlying compute power that people need for that. Actually, like, getting like an 8 GPU system and stuff like that of, the latest GPUs is quite expensive when you look at CapEx versus OpEx of just like renting one online for a little while. So a lot of that stuff is in the cloud. That's always kind of a Byzantine problem because the cloud is always configured, by default to cost you the most maximum amount of money. And so for a lot of small HPC sites, that ends up kind of being a barrier to entry. Figuring out how to tinker with all these different options and stuff to make sure that they're being able to minimize that cost. Whereas, a lot of these people are far more familiar with kind of the financial setup of building one of these big systems like that. So overall, these days, like I said, with AI, just kind of it's a lot easier to just rent something online than it is to build a dedicated like massive AI system. So a lot of that's online. Even like P100s, V100s, some of the best GPUs of yesteryear are rapidly aging out of usefulness. And so, yeah, in that case, it's kind of a lot in the cloud.
I know we talked about this before, Gary, Alan. From your perspective, are you guys using cloud? I mean, you have pretty large on-prem environments, but are you bursting to the cloud? Are you leveraging cloud as the place to run specific workloads? What does that look like?
I should let Gary answer first. My answer is no, but I want to hear what Gary has to say.
Our cloud use is increasing, so we actually do make good use of the cloud. I think, though it kind of runs not in conjunction with our on-prem. Let's just say it runs parallel to the cloud, because people don't burst out from on-prem to the cloud. They just kind of we don't like having institutional things set up in the cloud for people, other than the fact that we may have like an AWS organization so that we can manage all the accounts. But most of the people are just using the cloud tools to spin up something and running it that way. Whereas, and it makes it harder because we don't know how they're running their job. We don't know how it's performing. We don't see, other than the cost. We just maybe see the cost. So a lot of our focus is on the on-prem. And because the institution considers computing an essential component of supporting research, then it is subsidized. So it is a big cost advantage for researchers to use the on-prem resources, because they not only get it, is it cheaper, but they get the support from us too.
So some of the people I've talked to use the cloud first, in some cases, because that's where the data lives. If it's shared data from someone else and it's cheaper to execute there than it is to bring it in-house, is that still the case?
Yeah, we see that, yeah, because a lot of times it's really fast, especially with our consultants. They'll say, oh, yeah, if you just use AutoML, we can just get this going here, and then they'll try it out and say, oh, yeah, that works out great, and then maybe, and we'll let them go. And then maybe 9 months again, they'll show up and say, well, actually, I'm using it a lot. It's costing me a lot of money. And then help them move it back on-prem.
Yeah, so that's been my experience. The but is that I've requested a cloud research budget for 3 years running, 4 years running. Never gotten it approved by management because I've done too good a job of convincing them that we deliver better ROI on what we do. Sometimes you're your own worst enemy. I actually run a whole cloud center, and we work a lot with companies helping them use the cloud, and we can't do it at home. What's the old saying? A prophet is without honor in his own country, or something. But I think Gary said it right, that people will go and experiment. I do want to push back against one thing we've said a couple times, that bursting to the cloud is easy. I've heard, don't have direct experience in this, but I've heard from several people who've been trying this, that it's not easy for them to burst, that you have to make, especially if you're trying to use spot instances, you have to make a lot of complicated reservations. You have to get AWS or whoever, Google or whatever, approvals to scale. Perhaps they've been burned too often by customers inadvertently running up big bills, and they don't make it as easy as they used to. And I was surprised by this, but it does seem to be recent feedback that that scaling is not as easy as you might think. It is something you have to do in a more planned way than people might be aware.
Thank you, Alan. Justin the Rose, because I was
well, I mean, I just was looking at the time because I was going to ask a follow-up question, but I was like, I don't know if we want to keep just diving in. I think we could probably go forever here. So maybe just to do a little clarity. So on Dave's question, just as I'm understanding it, so he's asking about the difference between in-house hardware, leased hardware farms, and then the big cloud providers, AWS, etc. We know what the major ones are. And then he says, for each of these cases, what is the best source for HPC support? Or is that outside the scope of best practice discussion?
Jonathan's laughing. There's a lot of answers to that one, in my opinion. But Jonathan.
So I don't have any specific experience with leased hardware. And what I have seen is like leased hardware in your own environment. So that's more just a cost question. And it's functionally the same as on-prem. And even if it's not, even if it's someone else's data center or you have it in a colo, the actual performance characteristics should be the same. It's dedicated hardware for you, and you're running on it. And there, we'd love to talk with you here at CIQ, of course, for your HPC support in either of those environments. Frankly, any of them with cloud as well. But a lot of it is the same, regardless of where you are, especially if you're talking in an HPC context. But there are things that are better to do in different environments. But the thing that that I think anyway, that you're optimizing for in each of those scenarios isn't just getting the most performance out of it, because that's roughly the same in all of those environments. You look at your environment, you see what you have, you benchmark your application, you can make changes and see if it gets better or worse, and iterate to success. But when making this decision of like whether to run on-prem, whether to run in the cloud, to me, that's just another optimization problem. One of the reasons people like to develop in the cloud is because they're optimizing for latency. If every time you wanted to do a new project, you had to wait for a whole new data center to get built and a cluster to get put into it and budgets to get approved and all of that to happen, then your time to solution is crazy. But you can just put in a credit card number and have a new GPU right now to try it out. But when you are running in that environment, ultimately, like there's no free lunch, right? Your research computing, as we often are talking about in an HPC context, is an optimization problem for trying to get the most compute out of the least money, usually. And that usually means you're making trade-off decisions about not actually needing enterprise-grade services at all times. And when you're in the cloud, you're usually paying for enterprise-grade service at all times. There are exceptions like spot instances and things like that. But even still, the way I like to look at the cloud, and I think I've said this on the webinar before, for research, the value of the cloud isn't that it scales up. Because when you scale up, you can do it more cheaply yourself. But it scales down, and you can get the reliability and the performance of an enterprise-grade solution, but just a little tiny piece of it for your experiment right now. But if you're going to run a lot of it, then it makes sense to move it to something on-prem. And there are going to be performance characteristics infrastructure differences in those two environments, and you'll have to prototype and benchmark and build your use case against the environment that you're in. But it'll be different from one cloud to the next. It'll be different from one cloud's instance type to the next. And then it'll be definitely different from one on-prem cluster to the next, because there is no standard. Everyone is different.
And I'm going to toss in one thing here that about getting readily available from the cloud. For some things, let's just say today, it's harder to get like a large number of the latest NVIDIA GPUs in a cloud in a block to do like training LLMs, for example. And then so if you went to ask for that, then it's not something that you could just jump on and use today. There'd be like a few months wait for that.
So absolutely, and certainly compared to the way it once was, that is the sensation as AI research in the cloud has spun up and everybody is trying to do it. But compared to if you're coming from nothing, if you don't have any compute available to you, you don't have GPUs in your infrastructure, you don't have a data center, the latency of a few months wait in the cloud is still lower than a year or more of procurement and waiting for budgets to be approved in that way.
It never takes that long, Jonathan. Come on, a year? Kidding. So while we have a little bit of time left, this is something I know that Alan is passionate about, and I would like to talk about. When we talk about energy efficiency, and from a performance perspective, you could look at maybe not the fastest return of data or the fastest execution of a job, but the most energy efficient use of a cluster to get a result. Let's talk about energy, Alan.
Yeah, so as I say, most schedulers not only can return I/O performance statistics, but can be set up to return energy usage. And I think it was Professor Matsuoka Reiken that announced at the last supercomputing before this one that they were going to start allocating the Fugaku allocations in terms of energy consumption rather than core hours or anything like that. And this would
real smart.
sort of,
That's cool.
yeah, would cause people to look a little more carefully at the energy efficiency of their code. It's a very multi-level subject. But one thing we can probably note is that in the pursuit of the AI hype, we seem to have thrown this consideration right out the window. And instead, we're talking about 100 kilowatt racks and stuff like that. To be fair, you only really need that kind of performance for the ingest route, the training part. Many inference or other derived uses of AI really not energy consumptive or even CPU or GPU consumptive at all. So it's really the Bitcoin miners and the AI trainers that are responsible for our planet slowly melting, right? Or quickly melting. I guess one way to frame your question, Zane, is how can we achieve this, pedal to the metal performance that we want at better energy efficiency? And I think there's some very hopeful things on the horizon, or even already being deployed. The ARM processors have been setting new records for performance per watt, and RISC-V, yeah, it's like it'll be ready soon, real soon now, right? Trademark. But there are performance improvements, and NVIDIA has invested heavily in ARM technology and FPGAs, so we may see some improvements. For now, though, I've actually taken to on my social media chiding my friends, pointing out there is no AI. There is no AI. It's all obscure scripting with unexplored failure outcomes, or plagiarism as a service, right? So quit burning the planet up to do this stuff, and get back to work. But I think one way to phrase it is, what the value are you delivering to your organization through each mechanism, and can you optimize the energy impact of that in some way?
I just imagined a recycling ability, right? With all the heat that is produced, being able to harness that and then use it somehow, some way. Anyway, someone will figure that out. Someone smarter.
I think that the National Renewable Energy Lab, NREL, that's down the street here in Golden, actually does that kind of thing. I think they run their hot water from their cooling system out to do snow melt and things like that.
That's awesome. I mean, awesome. Just really, it's it's amazing all the things that are created with HPC resources. And I think I'm going to cut us off now, guys. I love you all, like, to the moon and back. It is really good to see all of your faces. You're wonderful and beautiful, and I'm so glad that you are here. At CIQ, for all of you guys that are watching, we are more than happy to talk with you. Like, part of Dave Rush's question is, was talking about HPC support, and that is kind of what we do. So you are welcome to come chat with us. Jonathan, Brian, myself, Zane, Forrest, and the rest of the team would love to talk with you guys. We do have our traditional HPC stack, and again, on the website, you can get lots of information there, all open source. We got the Rocky, the Aptainer, the Werewolf. And of course, Alan, you talked a little bit about automation, and we have recently, as a company, just did a nosedive into automation. And so we would love to chat with you guys about that as well. So definitely reach out to us. Make sure that you like, subscribe, share this with somebody. If you guys have another question that we didn't answer, go ahead and pop that in the comments below. we're always looking at new comments that come up and trying to reach out to you and answer those as best that we can if you have an idea for a topic that you want to have covered as well. So yay, we're so glad that you were here. Oh, and we have a podcast now too, right? Flops and Threads.
Flops and Threads.
That's it, man. Yeah, check out our new podcast as well. All right, you guys. Well, thank you so much for listening. We'll be back here same time, same place next week. Have a great day.
Thanks, guys.
Bye.